Release. Hi, this is Kaylee, and let's talk a little bit about moment of inertia and what that means. Basically, moment of inertia is the rotational equivalent of mass. So, inertia is a good word for it. And depending on how it's structured and where the mass is, we can get different things. So, for a mass on the end of a string or end of a pole or something like that, the moment of inertia is determined that all the mass is way out here away from that point that it's rotating about. And so since all the mass is concentrated out there, then the moment of inertia, when we use I for moment of inertia, is the mass of the object times the radius that the mass is out to squared. And that's the basic one to go by. And moment of inertia is weird. The unit is kilogram meter squared. So what if we get something different besides this, where all the mass is out on the end? So if I get this swinging around, if I spin it really fast, it looks sort of like a hoop, which is another thing that has the same moment of inertia as this, or at least how the equation. So if all the mass is out here on the edge, as far away from the rotational point as possible, so pretend this is rolling, then the moment of inertia is still mr squared. But what if we take this mass and we pull it in so there's an even distribution and we make it into a disk, like this one? Now things have changed. Now you don't have all the mass at the very edge. It's evenly distributed between the entire shape of the object. And so that changes the moment of inertia. So for a disk, it's actually 1/2 mr squared. Almost think about it like this. If we kind of squish it down, to make it sort of look like a hoop, the mass kind of fills in this place here. And it's a little bit halfway through. Not a good analogy, but it may help a little bit. But this is where all the mass is distributed on the very outer edge. This is where it's evenly distributed throughout the entire shape. Well, what if we do, instead of a disc or a cylinder, how about a ball? So, for a hollow shell, like a regular ball, like a tennis ball or a basketball or soccer ball or something that's hollow in the center, then the moment of inertia is 2/3 mr squared. But if it's solid, now we got that whole even distribution, we actually get a smaller fraction. It's 2/5 mr squared. So, I wish I had ones that are the same size or in the same mass. But this one, because it's evenly distributed, would actually be able to rotate quicker. Because remember, moment of inertia is the equivalent of mass. So the smaller the moment of inertia is equivalent to the smaller mass of the object. So less mass means it's easier to accelerate. Just like a smaller moment of inertia means it's easier for it to rotate. Now what about if we have something that's not circular in nature? So what if we have a rod, and let's say the rod's going to rotate about its end like this. So it's not quite a mass at the end of a string, because we do have mass evenly distributed all the way through, but it's rotating about the edge. Well, it turns out we actually use the length. We're not going to use radius, we're going to use length. It's 1/3 ml squared, where L is the length of the rod as it goes through. Now, this is like a door. Picture a door swinging. So it can be a whole pane like this. That would still have the same moment of inertia. We still have the same, we have an L, and we have the mass of this. So, a rod swinging about the end, same thing like a door swinging. But if we swing it around the middle, that's much easier, because now you're swinging it around more like the center of mass of the object, if this was a uniform distribution. And so then it ends up being 1/12 ml squared, where again, L is the length of the bar. It can turn easier that way, not having to move the entire mass like this. So you've got a little bit of counterbalancing going on. So what happens is, we're still going to use L as the entire length of the bar, but picture this. If we just had half this bar swinging, just ignore this part, okay? We have half L. Well, if we put half L in this, 1/2 squared is 1/4. 1/4 times 1/3 is 1/12. So it's a way you can kind of remember the difference between it rotating about its end and rotating about the middle. Okay? But moment of inertia is about the mass distribution, its shape and the distribution of mass. The further out the mass, the greater the moment of inertia. The closer the mass is to the point that it's rotating around, the smaller the moment of inertia. One of the reasons why there's a difference between a ball shape, like a sphere, and more of a cylinder is think about how this looks. See here, all the mass is still that radius from the center. But for a ball, if we could cut it in half, you see that there's some mass on this side, but the mass is kind of going in until it's around that point that it's rotating about. So because of this, that turn there, we get a slightly smaller moment of inertia for those shapes. All right? So again, think about the distribution of mass and how far it is from the point of rotation. All right? Thank you. And tune in again and we'll do some races with these objects and see how moment of inertia will help determine which one wins the race as they roll down a ramp. Thank you and tune in for some more physics. Bye.